So my project presentation is probably going to be a bit more chaotic compared to Hannah's and Daniel's, but I worked on a problem called disaster resilience, but pretty soon into the project, I kind of branched into my own little mini project, which relates to it in some way. It's to do with graph theory, which I think a lot of you guys will have heard of as a Melbourne Uni subject, which touches on it or looks at it specifically. But I'm going to walk you guys through a proof that I went through basically for 3 of these 4 weeks, once I got my head around the problem in general. And I just set about kind of proving this theorem of sorts, which I hadn't found online anywhere before. Yeah, and I ended up writing up and hopefully maybe one day publishing. But if I just, this is the poster, but the actual paper which sort of describes it in the depth that's required is just linked here. And it's like 7 or 8 pages as it is at the moment, unedited. So what I'll do instead is just share my screen and kind of walk through it quite casually, which I'll do on my own laptop. Okay. Yeah. All right, so the main concept which this touches on is the connectivity of a given graph. So if I draw, for example, this graph here, its connectivity is going to be 1. The reason why that is because if I remove one edge, it's going to break up. So if I remove this edge, it's going to break up the graph into 2 connected components. So it's going to be an isolated subgraph, that being this node here. So this graph here is 1 connected. If I draw a second graph, say this one, this is going to be 2 connected. The reason being is that if I remove this edge, that's not going to disconnect the graph, nor would any other removal of an edge. I would actually have to remove 2 edges, so this edge and this one, for it to become disconnected. So this is 2 connected. In fact, if I draw any cycle graph, which is effectively just a circle with some number of nodes, so this is the cycle graph with 5 nodes, this too is 2 connected. I can't remove one single edge such that it disconnects. I would have to remove 2. So my theorem states that given any cycle graph, if you wanted to increase or add edges, or augment is the word they use, edges to that cycle graph to make it 3 connected, and you have to do so such that no 2 edges overlap. So the graph remains planar is the technical term, and you have to add all of those edges within a single face. So within the cycle in this region, see that? Yeah, you can. You would have to add at least n-1 edges, where n is the number of nodes in this graph. So you can kind of try it yourselves. If I want to add edges to this graph on the inside face, the outside face, it doesn't matter, but it has to be a singular face. Where no edges overlap, I would have to add 4 edges because there are 5 nodes here. So if I just grab a new color and go 1, 2, 3, 4, for example, this is now 3 connected. I can't remove 2 edges such that disconnects, so it's 3 connected. I cannot, however, make it 3 connected by adding only 3 edges. So if I gave that a go, like here, here, and maybe here, then I could remove this edge and this edge to make it disconnected. So in this situation, it's still 2 connected. I would need 4 edges here, and in general, n-1 edges to add. So the proof of this was, I started out by setting it into 2 sort of mini proofs. The first being that it will take, so the minimum set of edges to add is at least n-1 of size n-1 was one half of the proof. The second half of the proof is the minimum set is at most n-1. So to prove that the minimum set is at most n-1, my proof was just to show that if I double every edge here, this will preserve the planarity of the graph. So there's no overlapping. Every edge except for one. It will also make it 3 connected, and it's all going to be within the single inner face. This graph now is going to be 3 connected, and it's used n-1 edges, 4 edges for this pentagonal shaped cycle. So in any situation, if you double all edges but one, that's going to make it 3 connected. So it's going to be at most n-1 edges that this minimum solution, this minimum set of augmented edges is going to need. The more difficult part of the proof was proving the lower bound, that it takes at least n-1 edges. If you guys try and do it in your own time, you'll realize pretty quickly that yes, it will be n-1 edges, but the proof of it was a bit more complex, and hence the 3 weeks that it took me. I'm going to stop sharing now and just work through the actual paper or draft paper. Yeah. Okay. So this is the proof that doubling all but one edge is going to make a 3 connected. It's fairly simple. And yeah, it gets a bit more complex here. So I get my head around where I started as well. This is getting a bit chaotic.
Don't stop share.
I think I might, and then do it on here again.
Okay.
Yeah. Oh, sorry. I'll be really quick. So let's start with let's start with a clear screen first of all. If I have a hexagonal cycle, we know currently that this is not 3 connected. It's just a cycle which has more than one node, and so it's not 3 connected. That's another sort of sub-proof which I had to work on for a little bit of the paper. And so we know at this point we have to add at least one edge, right? So we're going to add an arbitrary edge between 2 arbitrary nodes, which I'm just going to draw here as E1, though E1 could sit, for example, here as well, or here. E1 could be anywhere, but for the sake of it being arbitrary, we're just going to draw it in there. Now we've added one edge so far. This next maneuver is kind of central to the theorem, or the proof of the theorem. That is, what we're going to do from now is actually convert this and pinch the graph and convert it to something which looks like this. So we have removed E1 from the graph, and we have now this pinched graph. Now, the sort of majority, or at least a couple of pages of the proof, kind of worked on establishing the fact that in order to make this graph 3 connected, you need no more edges than the amount of edges to make this 3 connected. And so as a result, we're actually going to end up working on this graph here, and then getting the result and using it to prove the lower bound of the minimum set for this graph here. And the problem actually becomes recursive, as you'll see later on. But the other reason why we can pinch the graph and continue the problem is because, of course, once this arbitrary edge E1 has been inserted, we can't actually add any more edges across the subgraphs. So I can't add an edge like this because that will violate the planarity of the graph. So pinching the graph is not going to increase the number of edges we need. And it's also not going to remove any potential additions of edges, because if we wanted to add an edge between 2 subgraphs anyway, that would violate planarity. So here we are at subgraph P. this problem actually turns into a fairly simple one. The reason is because if we wanted to make this graph disconnected, so to be clear, if we wanted to disconnect P by removing edges, more specifically, 2 edges, because that's the test as to whether the graph is 2 connected or 3 connected, we cannot remove an edge from this top subgraph and one from this lower subgraph. That in no situation would make it disconnected. If I try doing that, say I remove this edge here and this edge here, it's still going to be connected, right? And that's, again, like a sort of mini proof I had to include there, but it's fairly straightforward. And so the problem becomes, I want to add edges to this subgraph here and this subgraph here, such that each subgraph is 3 connected. So long as each subgraph is 3 connected, then the whole thing is 3 connected, because you can't remove an edge from the top and the bottom to make it disconnect. Again, to be clear, I could, however, if I don't want to remove this edge, I could remove this, edge here, and it becomes disconnected because this node is now isolated. So I'm aware of time, and I'll just go into the next stage, which is to make each of these subgraphs connected. And so this problem becomes recursive because we're applying the same algorithm to both this subgraph and this subgraph, because the overall P graph is 3 connected if and only if both its subgraphs are. I'm going to stop sharing and finish sketching finally and jump onto the screen share just to show the final step of the proof. Share screen. And this final step actually uses strong induction, which, I mean, if you guys have done real analysis, you look at induction, but strong induction was something I had to familiarize myself with. What we have here is, and it gets a little bit out of touch here, but the number of edges needed to connect the original graph, so the non-P graph, the one on the left pre-pinch, is greater or equal to the number of edges we need to make the top subgraph of the pinch graph 3 connected, plus the number of edges to make the bottom subgraph of the pinch graph connected, plus 1. We plus 1 because of the arbitrary edge we added initially. And we have greater or equal to because of the fact that the original graph uses no less augmented edges than the pinch graph does, which I touched on before, which is its own like mini proof, which was complex, and I still have to work on it and really make it cleaner. And so we have this relationship here. We also have this base case whereby if we have a subgraph of node 1 that is trivially or by default 3 connected, you can't remove edges to make it disconnected anyway. So that's our base case. And we can solve this inductive relationship with the base case and the inductive case using strong induction to end up showing that h of n, the number of edges needed to augment the original graph to make it 3 connected, is at least n minus 1. Not equal to n minus 1, but at least n minus 1. But that doesn't actually matter because we have also proven at the very start of this that the upper bound on the minimum set, on the size of the minimum set of edges to augment, is n minus 1 as well. So if the upper bound is n minus 1 and the lower bound is at least n minus 1, then the lower bound too has to be n minus 1, no more. And with that, we've proven both the upper bound and the lower bound of the size of the minimum set to augment edges to make it 3 connected, and thus the theorem is proven. Yeah, so I was lucky that the proof was kind of the right size for the 4-week program. I got a lot of help, of course, from Charles Raz, who was my supervisor throughout, and a bit of research into books and a couple of theorems as well, which was central to a couple of the proofs. But yeah, that's my presentation now.